Okay, so we left it previously at the point where we were asking what is important for us to store about a building so that we can have interesting, clever, automated processes on it. So how do we encode our information in data so that it's useful for us and for the processes that we want to run? We'll now move to completely different topics. Because there's something important to say about networks. All of what we've seen before is valid across the layers, so it's from the bottom of computing hardware and architecture all the way up. There are situations where you are working with several people and networking come into play. So today we look at the fundamentals of networking, because I believe that this is also an important part of what you need to understand to be able to design an IT infrastructure that will cope with the complexity of the interaction between the people that will be part of your building information modeling management plan. So we start looking at, again, from the foundation, but this is, trust me, this is the only day we are spending on so much low-level core problems. Then we move up to operational problems very soon. We're looking at the idea of networking. How does it come up? What is really networking? And the principles behind line and packet switching. The concept of a client server. The importance of defining protocols. So what a protocol is and what do we do with it. And then what are the common protocols? What internet, externet, and so on. We'll talk about briefly about security, firewalls, and cryptography, and all the safety features that you have to consider around your data. Okay? Can I ask you how familiar you are with some of these topics before we move on? Just minimum. Same applies for you?
Familiar with some.
You might have patched together a couple of routers in your house, or you buy an ADSL and you just connect and they work, and that's amazing. So networking is the idea of bringing together a couple of things with a line in between. That's very simple. Now, traditionally, this was actually physically done with a cable. So to put together two computers in a network, what you would do was to establish a physical connection between the two. You have computer 1, you have computer 2. They are in the same room or in two different rooms. You just physically snap in one and the other, and they start talking. And this is valid for any network. So telephones as well. Traditionally, you would have hubs where you would pick up the telephone and say, well, I need to speak to somebody in Pittsburgh. And all the way from you to Pittsburgh, people would be, operators would be kind of physically snapping in connections to put you in touch with Pittsburgh, right? So you need somebody in London, so you would pick up the phone and be in touch with London, and then there would be somebody snapping in a cable to put you physically in connection, so to attach your cable to another cable that was going across the ocean, New York. And then next to New York there would be another operator who would put you in touch with the line, and eventually this network would be built physically between you and somebody in Pittsburgh, okay? Snapping connections in. You've seen this in old movies, have you? Yeah. Or are you that young that you're gonna... Have you seen an operator switching? Really? Yeah? You haven't? Damn it! People like that, physically connecting, snapping connections.
A lot of parodies on it.
How old are you? Can I ask you, what year were you born? 89.
23.
Right. Okay. Now, the idea is that at some point you change from this logic of, cutting open this cable and, redirecting it to this other physically to talk between this and that. This is a complex operation, right? So we want to establish it, and there is somebody that needs to kind of physically do stuff. We don't want anything physical. We want things to be virtual. We want things to be ideas. Ideas are much more easy to move than cables. So how can you think of a situation where the network and the communication adapts to the people you want to talk to, regardless of the physical connection? Well, you think of a computer that is connected to another computer, that is connected to another computer, and so on. Clearly, communication can happen in a situation like that. But before you start talking, you need to add something to the communication, which is an address. The idea of the person or the computer or the service that you want to speak to. So it's not enough to start blabbing on this line. You cannot really start saying, what do you think? How was your day? That doesn't make sense, because you're not really wanting to speak to this guy. You wanted to speak to C5. So you have to say, could you please ask C5, how was his day? So if you look at the data that is going across here, previously, in a line switch, so if you were directly connected physically to the person that you wanted to talk to, you would just ask, how are you? And you could send a text like that, encoded in a stream of bytes. And you could say, well, H we know is 89, O is whatever else. So you build up a file, you send this file, the other person opens it and says, oh, well, how am I? Oh, I'm very well, thank you very much, and return. And then, bam, the information will be sent back. And bouncing up and down. Now, the innovation when the internet came about, the idea of packet switching is that you can speak to anybody you want. But in order to do that, you have to have everybody identified univocally on the network. So you have to send a message that is not only, how are you, but is, I am C1, I want to speak to C5, and the message that I want to send is, how are you? So you send the packet across. C2 receives it and says, it's not for me. It's not for me, I'm not C5, I'm C2. So I'll send it across to somebody else. So he will send it to C3. C3 will open it up and say, oh, this is for C5. It's not me. Close it down, send it across. Now, if this is clever enough, we'll send it only this way. If it's not clever enough, we will send it both to C5, to C4, and to C2. So stupid. You send, you just told me and I'll tell you. It can be. It can be that it sends to everybody he knows, right? If it's clever, it's just sent to the right person. Now, it must be very clever, because the situation here might be that the network is very complicated. So it might be that it's not in direct contact with C5. Say this is 17 and this is C5. Oh, so how can he know that C5 is a friend of that? So he will send here and there. It might be that this is connected here. So you see that the complication increases. It might be that this guy here send it both this way and this way. It's generally simple to avoid sending it back to the people that ask you. And then all of a sudden this sends to one, this sends to one, and then this guy here receives contemporary 2 messages from 2 people and say, oh, how are you? Who's that? How many times did I receive this message? Twice. Yes, but was it sent only once, or was it sent twice? Is it the same message, or is the guy insisting? So you have a lot of information that you add to it to say, well, I'm message number 22. So when I receive these messages twice, I say, oh, 22 is the same. I was always asked once, so I disregard one of them and whatever. Make sense?
Yeah.
So all of this is based on protocols. All of these people need to agree on the format in which information is sent. They need to agree that there is such thing as an address of the sender, an address of the receiver, some idea to identify that things are not repeated, a time and day of the moment where the message was sent, another time and day that tells that, well, if you haven't managed to submit by this time and day, drop it. It means that something is going wrong with the message and so on. All of this information, all of these procedures, all of these ideas of ways and rules and regulation on how to exchange these messages are encoded in a protocol, or actually in a couple of protocols that you call TCP/IP. You must have heard of this. Have you? TCP stands for? You must have done
It's the acronyms that I get confused, obviously, in protocol. Customer protocol.
No.
codes.
No. No.
Can't remember what it is.
It's not important really, but it's transfer control protocol and internet protocol. So the internet protocol is the way of calling computers with a name. Okay, so the way in which we identify individual computers on the network. And the transfer control protocol is the set of rules that we use to control the flow of the packets across the network. So we have a bit of it to identify who's who, and a bit to identify what are the rules that we agree and share in order for the packet to reach destination. That's straightforward. Now, 10 years ago, probably 10 years ago, computers were running on all sorts of networking protocols. TCP/IP came out to be a great winner over that. There are still hundreds of different protocols to handshake communication and send packets around. TCP/IP resulted in being the most efficient one, and everybody adopted that. So it's very uncommon nowadays to have any protocol on the network that is not TCP/IP. Everybody's on the internet. In current implementation, now you have a lot of legacy products, legacy infrastructures that are still running on old protocols. Right. All clear with this? Let's look at the IP portion of TCP/IP. Remember that this is the way of, we just said it.
They communicate the address?
It's the address, right. It's the identification of individual computers on the internet. Why is that important? Well, if you have two computers having the same address, you cannot tell to whom was the message initially addressed. So both will receive it, but this might result in problems. So it's impossible, according to TCP, according to the control and transfer mechanism protocols, the systems are not allowed, multiple computers are not allowed to share the same IP. Every computer must have a unique IP. Okay? How big is an IP address?
9 digits.
Nope.
11.
You might have heard of this.
No, no.
It's 4 bytes. Right? 4 bytes.
Yeah. Now it's just
There are sometimes, have you come across the idea of 192,
yes.
something like that?
That's
Does
what
that
I
sound
thought.
familiar? Yeah. How is this 4 bytes?
Because the 192 is one base, 168 is
Second byte, third byte, fourth byte, right? So they can all range between 0 and 255. 0, 255, 0, 255, that's the maximum, right? How many different computers can we have on a network then?
serious.
It's always the same question, guys.
We need different computers.
How many different computers can we have on a network?
200.
See again?
256.
We know it's more, right?
Yeah.
Because there are probably 256 computers on the network in this building.
256 is about 4.
Now this is important. I'm coming back to this because again and again you will find this question: what is the limit of my infrastructure? Okay, and the only way to address it is to go back to the binaries. So how many different numbers can you write if you have how many bits?
32.
So 4 bytes, 8 bits, 8 bits each.
256 is about 32 then, is it?
Nope. So how many different numbers?
Two exponential factor.
It's always the same rule, okay?
Yeah.
Now, you count how many bits, and then you go 2 to the power of that many bits. It's very simple, but you have to get into the habit of trying and thinking about that. So, how big a number is that?
Massive.
It's large. It's large, yes.
Oh, good context.
So it's about 4 billion.
I'll give you that, yeah.
Give or take 100 millions.
208.
All right? So, why is it not 4 billions? Well, it's less than that. It's less than that because of the way in which blocks of IP have been given out to people. Now, remember, we have to guarantee that IPs are not reused. So, the only way to guarantee that is that somebody will have authority to assign these IPs to people that can use them. So there is an authority, I think it's called IATA, that gave out these blocks. So told people you can use the IP starting from 1, 2, 3 point something that you up to this other IP. You bought it, okay? And there are some IPs that are invalid. They are kind of magic IPs. They do some specific functions. They mean tell everybody or some other rules like that. So actually we have less than 4 billion IPs, and of course we cannot use all of them efficiently because people want to retain some safe IPs for expanding their networks later and so on. So they're not all used. Basically, the problem we're facing right now is that we are running out of IPs. The internet is running out. All the blocks of IPs that were available have been sold already. So if you want now to call the IATA and ask them, can I buy 256 IPs for my computer network? They will tell you, sorry, no. What you can do is try to buy them on the second-hand market from somebody else that don't need them. They have bought them in the past and don't need them, so you can buy them from them. Now, of course, IT comes with problems and solutions. So the problem we had in the past is that these 4 bytes were completely used, so a new standard came out so that we can now use another version of the Internet Protocol that uses 128 bits. It used to be 32, remember? It's now much bigger. So, with this new version of the protocol called IPv6, have you ever heard of that?
Come across the acronym, yeah.
IPv4 is the one that uses 32 bits. IPv6 is the one that uses 128 bits. How many IPs can we have if we use all of those bits, all of that 128? It's always the same question. It's 2 to the power of 128. How big is that? That's huge. That's huge. That's not 4 times bigger. Because you don't have to make the mistake of thinking that since it's 4 times as big in terms of digits, is 4 times as big in terms of combinations. It won't fit in your
I'm going to try.
Screen.
I'm going to try.
1, 2 here.
Yeah. Yeah. It's huge.
3.4 times 10 to the power 2.
Yeah. So you have how many? 38, you say?
Yeah, 10.
So you have a digit followed by 38 zeros. That's how many computers we can now connect to the internet if we use IPv6. We'll have 4 billion computers for each of us, something like that.
Really? Yeah, really.
Yeah, I think so.
Yeah.
Still useful because we're out
But
of
then again,
traditional IPs.
then again, you go back to the age-old question when you were talking about the binary and stuff. You've got the processing power, but you don't have as many inputs. So, is it necessary?
Well,
It's future-proof for us.
it's future-proof. When they did it for 32, they thought this was future-proof.
Yeah.
You have certainly heard that the CEO of IBM said, "I think there is market in the world for 5 computers at some point." At the beginning of the 20th century, IBM started to form as a company to produce hardware, and they said, "Well, there is probably market in the world for 5 or 6 computers. I have them on me now, right?" So, future-proofing is an important part of information technology. This is all software. IPv6 versus IPv4 can be dealt with different application, but there are hardware equipments that have been kind of where some of this software have been hard-coded. So there are some hardware equipment that can only deal with IPv4. So if you want to switch to IPv6, you have to kind of throw that away and bring in a new piece of hardware.
Or just do a piece of recycle it.
Yeah, you can recycle it, of course, but it's going to be expensive. Okay. So we are now at this stage where all the IPs have been sold, and there is a need in the future to move to another infrastructure. Apparently, 1% of the traffic on the internet is currently running on IPv6. The remaining 99% is still running on IPv4. So we are in the middle of a transition. This bigger number is being adopted because there is a view that we are going towards a situation where onto the network there are going to be a lot of devices that are not used by a man, they are not used by a human. They are going to be independent. They're going to run their own business, run their own algorithms. Okay, you might have a telephone, a traffic light on the internet. So a traffic light that is connected to the internet and will know whether a car is coming by. It will talk to the car. You won't go talk to the person inside the car. The person will not even be aware of this. You talk just to the car. And the car will tell, can you please make a green light for me as I'm approaching in 5 minutes? And you say, wait a second, I have to talk to everybody else before I can do that. And so we talk to every other car in the range, and they will kind of handshake what is the best way to switch red, green, and blue, or whatever colors the traffic lights will be by then, so that everybody goes without interruption. Right? And this is called the Internet of Things. Have you heard of it? What? Internet of Things.
Internet of
Have you heard of this sentence before? It's an expression that says in the future there are going to be more communication happening between stuff than between humans. This is the view.
I'd agree with that now.
It's probably already the case now, yes. But currently, all of these machines are mediating queries that are initiated by humans, and in the future this is going to be transparent. You don't know that your car is telephoning the traffic lights to let you go through. So this is why we are now facing this type of shift, technological shift. This is ARPANET as it was in 1958, I think. So the initial engine of the internet was like this. And then this is the evolution of hosts on the internet in time. How do you call that curve? It's an exponential curve. So every year we are doubling or so the number of connections. What's happening?
Pen rules.
All right. Okay. We've sorted the infrastructure, okay? We now know that there are ways to give each computer an address, and then it's possible in this monolithic network to kind of route packets of codes and information between all different players. Now that we know we have this infrastructure to send messages, what can we do with that? Now, there is a concept of a peer-to-peer network where all the nodes have the same role. So a telephone network is a peer-to-peer network. You make a number, then a telephone is just as any other telephone. The functions that the telephone provides, you can speak and the other person can listen to what you're saying, and vice versa. So the role of the two is equivalent. Okay. There is then a different approach whereby the services provided by the two people communicating, now forget that there is in between all the rest of the internet, forget about that. We can now abstract that out and say that we have different computers talking to each other. It doesn't matter how. Now, it's interesting to say that now these two can have different roles. One can be a server, and one can be a client. Have you heard of the client-server architecture before?
Come across it.
So, in a client-server architecture, there is a software that is capable of requiring some services, and there is a software that is capable of providing these services. The guy that provides the services is called a server. The guy that requires them is called the client. All right? Can you think of a client-server application that you use every day?
Skype, example.
No, tricky.
Yeah. AutoCAD.
Nope.
No.
Every day.
antivirus?
Yes,
They serve
Partially.
you with the
Partially.
protection.
some kind of clear-cut client-server application. You use them every day.
Shops.
No. The phone, you said? No.
Shopping.
Shopping. Yes. So any web server. We call them web server because they're servers, and you are web
I just
client.
meant scissor form shopping, but
So when you go on Google, you are querying a server. Basically what's happening is that you are a client and there is a server somewhere and you ask a question. Can you send me some information about this query? And they will reply to you. So what you do as a software and what Google does as a software is significantly different. They can answer your question. I mean, the software running here is capable of answering the question, and the software running here is capable of querying that question. Makes sense? So there, it's an asymmetric communication. The two applications are different. Are you following me on this? Skype is even more complicated. It's a multi-tier application. But let's assume that we had a peer-to-peer application to talk over the line, say Google Talk, for instance. The application will be like something like this. First off, you need a server to be able to know which of your friends are connected on at the moment. So there is a central place that stores what is the IP address of Claudio, what is the IP address of Kieran, okay? And then when Claudio logs in, he will tell Kieran, look, Claudio has this IP address. So we now know of all our friends who's online. And who is it that told us? The server. So there is one person we know we can call to ask who's online.
similar to like Microsoft Messenger, isn't it?
Absolutely, yes.
It's
Absolutely.
separate.
So, once we have asked that question, we can now talk directly to the other clients. And now we know that this is a peer-to-peer communication between you and me talking. And it's a symmetric process. So the language we are talking, we can both speak and understand. So we can we can ask we can query a service and we can respond to the service on each client. The server has a different role. It will never ask you to do something. It's there to serve something from you. Never gonna ask you stuff. Make sense?
What's that process called? Multi-tier, did you say? What's that? Server to client, and then what's this one called?
Well, it's client-server versus peer-to-peer.
Okay. Sorry.
There is any way that without server, I mean, I serve you and I require you at the same time,
Yes.
and you the same serve and
But
require.
there are network modes that operate without a central server. So, you can think of a possible scenario where everybody of this network knows of all the others that are connected. All right? The protocols that it must be able to deal with are much more complicated because of a server, you can expect of it to be reliable and always there. So, when you first connect to the network, you ask the server, and you know the address of the server, right? The server has a name, and you can always get to that name. You know that its address is 128 point something, all right? So you always ask, please 128 something, tell me who's on, and the list comes back. Now, if you don't know that there is such thing, who do you ask? All different people might have changing addresses, okay? So, you can start asking anybody. You know that you're connected to some other physically, and you ask, excuse me, do you know whether Kieran is online? He said, I don't know, ask the other guy. And you start asking randomly around, please, who's online? Until you find somebody that is online and you say, oh yes, I know Kieran, he's online. And then you start talking to that one, oh so good, thank you very much, who else is online? Can you tell me? Oh well, I have to ask everybody else. And then the network is dynamic and everybody talks to each other to ask whatever information they have, and it's a distributed system where everybody is acting as a peer. Now, to be participating into that, you have to pay the cost of being answering people who's online, because at some point somebody else will come online and will start randomly to ask around, and maybe they'll ask you, who's online? You go, oh yes, I know who's online, here's the list. So your software must be able to act both as a server and as a client. It's a distributed server in architecture. It's just that you start knowing that there are different roles in a network. Sometimes some nodes in the network might have more important roles than others. Okay? Even if physically they're just all the same. They are only just computers attached to network connection. Alright? Yes? So these kind of set of rules to say, so that we can agree on a way to ask the question, who's online? And we can agree on understanding the reply, well, such and such people are online, and they are available at this address and so on, need to rely again on arbitrary protocols, arbitrary ways to interpret the stream of numbers that we receive into a meaningful information. Okay? So the same that was valid for the file format, so we agreed on a standardized file format, is to be agreed on a way to discuss about things between different tiers. Alright? When you talk about protocols, that's what you're talking about. The set of rules that we agree to abide by in order for us to be able to exchange queries and answers online. Okay? Which of these protocols have you heard of? Have you heard of
All of them, I think.
DNS, FTP, HTTP? Yes? All of them. So I can ask questions. No. DNS, Domain Name Server. What is that? What does that do?
It communicates with you.
Huh?
That's the gateway towards you, isn't it?
It's a gateway in a sense. It's not a gateway.
Sure.
It's so close. So we know that every computer has an IP, an internet address that is made of 4 bytes, right? So when you go and digit www.google.com, who are you talking to? You're searching for something, but your client, your browser, which is a client, okay, who is he sending the request to? I mean, of course, Google, but who's Google? How can you... Who's Google? What is Google?
Company.
Yeah, but physically, on the network. What? Okay, I'm a computer, I'm stupid, I don't know anything about Google. What do I do? Who's Google? Google is just a name.
Yeah.
I don't know anything about names. I only know about IP addresses, right? I'm a computer.
The searcher.
But what
So the domain name server is that just it's a tag to attach to an IP address.
exactly is the thing that transforms a name into a number? So is the guy that I I ask, what computer IP is Google running on? So I ask to this server, do you know the address of Google? And he replies, oh yes, Google comes at 127
So you're asking a question.
12, 17, 8, whatever. So you're asking, the first thing you know, the first thing you must know before you can get to ask Google something is, what's the address of Google? All right? So when you type something like that, the first action that your computer performs is to call a server that will reply with the address of Google. And then it will ask Google to give it the initial page. Make sense? Now, how can I get in touch with the first server? I cannot call it by name because he's the guy that resolves names. So I must call it by number. So I must have this idea of a specific computer online that is capable of giving me a number as a function of a name. If you go and configure your network device, it will ask you for your DNS server. You must know its number because you cannot call it by name. Because he's the guy that transforms a name into a number. So if you don't have it, you cannot ask it, what's the number? Make sense? All right. So this is what the DNS is. These protocols here are for, so there's going to be a language that we share with these people on how to make a call or how to transform a name into a number. And these are the protocols that we use to exchange our email. So there is a server somewhere that will transform, that is capable of understanding questions such as, hello, I'm Claudio, my password is such and such. Do I have any new email? And he will answer, yes, 4. Okay, thanks, can I get the first one? Here's the first one. Thanks, delete that one please now, I've stored it on my own. Is there any other one? Yes, you have 3. Can I get the first one? Thanks. So this is a kind of communication that is happening, and all of this is encoded into a protocol that is called POP and SMTP. SMTP is a different protocol that allows you to send email. So that's the protocol that says, hello, I'm Claudio, my password is such and such. Please send an email to Anna saying that I miss her very much. Okay? FTP, File Transfer Protocol. It's a protocol that was historically used to just exchange files between different peers. There's going to be a server. You talk to the server and say, well, create a new directory of such name. And then in that directory, put a file with these contents. Thank you very much. Goodbye. HTTP. You must have heard of this. What is that? I won't go on until you tell me what HTTP means.
Waiting for the QI.
Never heard of that. You must have heard.
Yeah.
So,
Stuff, yeah.
H stands for
Hyper.
hyper, yeah.
Text. Transfer.
It's on the board, mate.
Hypertext off.
Yeah.
That's why I was trying
Sorry,
to
I didn't know that. So it's a hypertext transfer protocol, of course, and I should take it off the slides. It's the protocol that overlooks at the transfer of hypertexts. So an hypertext is a web page. Now, that only overlooks the transport, so the way for you to ask and for me to give an hypertext. Then, once you have received it, you have to understand what it is, and you have to display it on the screen. And that is done with another language, which is the HTML. HTML stands for Hypertext Markup Language, and is a language that allows you to identify what parts of a text are have specific characteristics. So they are bold, they are with they are with specific font, they are an image, they are a button or anything like that. All right?
So,
The font is CSS anyway,
what's actually the difference between
but you can embed it anyway.
HTTP and HTTPS?
HTTPS we'll cover in a bit, and it's the secure version of HTTP. So it's the version of the protocol that is capable of cryptography on top of the exchange. So it will hide the content of the communication, make it impossible to read from people in between. So you have HTTPS when you're dealing with sensitive information, your passwords, your bank accounts, these type of things is probably transferred to you through HTTPS.
Real.
Yeah, it did it as
So
well
you
yesterday.
said
So my umbrella.
The umbrella.
Umbrella.
So today both bits went up and down.
Yeah.
Okay.
That sensitive.
The interesting question is, are there any BIM protocols that you know of?
No.
DWG.
Ah, no.
That's first up.
That's a file format, right? And it's not BIM because it's vector based. So DWGs contain vector shapes. It doesn't contain semantic properties of a building.
Or
When I say semantic, do you get what I mean now when I say semantic? Semantic means connected with information that I know that is complete to me. So going back to the idea of these lines being a door or this line being lines is a different semantic level. Okay? So building information models know that there is a wall and inside it at some point there is a door. And they can transform this abstract, highly semantic information into lots of lines and stuff, but because they know about the door. If this was saved in a vector-based format, the computer could not know that. It would see a lot of lines, it wouldn't be able to count the doors. It would be able to count the lines that you want to know. All right? It can tell you easily, oh, there are 34 lines. But how much do they cost? Cost? Lines? Lines are free. Right? The other one can tell you, well, there is a door. How much does it cost? Well, that type of door costs X. That's when I say semantically rich. I mean connected to other databases, intelligently aware of what is the purpose of that drawing, not the physicality of it. Okay? So, yes, there are a few BIM protocols around.
the Army's developed a few, the US using that BIM library.
There are a number of
That's
protocols.
probably
We'll
the
cover
most
them in the
famous
next
one
few
that we'll
days,
cover.
but it's going to be taking some time. Happy with the idea of a protocol? So a protocol is some type of agreement that we have on the ways in which we exchange services online. So we exchange the service of providing for emails to go around. We exchange information about hypertexts. We exchange information about what is the IP of a name and so on. You can think of infinite ways of exchanging these services. You agree on one and you define that into a protocol. Okay? I want to die.
No, I guess not, do you know? I've never really, I've always thought HTML was probably better used rather than XML.
Sorry, say again?
I've never really come across XML that much. But different ages.
So, I'm sure you have heard of HTML, right? So you know that you
It looks
open it.
pretty much like this.
It's similar, is it not?
Yeah.
It's
Different.
pretty much, but great difference semantically again. So I want to cover that aspect here. HTML is a specific language that was standardized by people interested in defining what ways to exchange hypertexts. Okay, so when you have when you have a text and you want to make it nice, you say, well, hello. What's wrong with my pants? I must have more.
It's one on the floor.
So you want to display something that says hello, and then goes, you now have three options. Press here for 1, press here for 2, press here for 3. Okay? So you transfer this into a file, and hello you want to show in big characters. So you, before you write hello in your file, you kind of enclose it in something that says H1. And this is a syntax for you to do that. You are going and hiding in the text something that is not shown on the page, but it's just a tag, something that says something is happening here that the computer should be aware of, which is that this portion in between must be shown with bigger characters.
Oh, you can customize it.
Yes, you can customize it, and the point is, to some extent, you have a limited amount of special keywords that you can use here. H1 means header of type 1, so a very big character, bold, and very strong. H2 means just a little smaller, maybe not bold, and I don't know, some. And you have up to 6. You can group this into 6 levels of headers. If you're not happy with that, you can probably use a font special keywords that says use this type of font and use it this big and so on. And then at some point that will end with /font, and everything in between will be displayed in italics or whatever you specified. Okay, it's going to be fuzzy.
You create a class and it's
Slowly. Now, you can do something about it, but the keywords that you can use are limited. There is an agreement between us on what those are. Okay? XML means extendable markup language. Extensible, I think. So this means that we can use any tag here, any tag that we want, and transfer this information across. Then separately, we can say, well, what this tag really means is that you should do something like that. So this gives us the opportunity to define a structure of the data that is arbitrary. It's not just about making things visibly bold or red or green or whatever. It's attributing them with a semantic connotation. So if this was an XML file, rather than saying, well, what follows is a text, you're saying, well, what follows is a quiz, really. You are attaching some semantics about it. We are talking about a question. And then the question is, who was the 42nd President of the United States? And you see that the question then ends, and the answer starts. And then you could have here other things that could say option 1, option 2, option 3. And then if I receive that information, I can start showing maybe the question with the 3 options. And then when people select the wrong one, say, unfortunately it was wrong. And when they select the right one, you'll say, oh, correct, this is the right question. So I'm starting to attach inside the file information that goes beyond how I want to display it. It's about what it is, its semantic value. Differentiating the question between of the answer, not on the basis of how it looks like, but on the basis of of classifying it in the code. The whole thing is a quiz. A portion of it is a question. There is an answer, and there are many options available. Okay, you're starting to be able to discriminate inside the document the meaning of different portions. All right, this is tricky, I know, but it goes back to one way of encoding information in such a way that, in such a data format that multiple people can read it. Okay, so XML is a standardized way of exchanging semantically rich information, and you decide what the semantic classes are. Not interested in quiz? Fine. You start with a tag that says, here comes a recipe. And then you say, ingredients are such and such, operations are such and such. Okay? Okay, the next step is, once you have set up a system where you successfully attached semantic value to the portions of information that you want to transfer, then you need to, and you have a protocol so that people can exchange that, and then they know that they have algorithms and functions that they can run over those data. You need to be sure that there is continuity, that those services will be reliable, stable, and working systematically for you. So you have to think about efficiency and redundancy. So is the system structured in such a way that the speed of the server to reply all the queries that it receives is fast to cope with the peaks? What is the priority of applications that if I am running multiple applications on my server, what are the priorities that it deals with? Does it only serve intelligent questions first and then stupid questions later? You make it up. You want to make sure that you standardize some service quality, so some reliable way of measuring whether the servers are replying timely to your queries. And there are contractual implications to that, of course. Redundancy comes into play when you have multiple systems that can provide the same service, and if one fails, then another one picks up automatically. So you have two servers online, say, that you can query, and you can send a query that goes, please give me, let's say it's an HTTP server. Okay? You have a number of clients here, and they all want to go on YouTube, and YouTube demands lots of transfer from the data. So you have big data streams coming down, big data. At some point, the server cannot cope, so it's going to crash. Another server will pick up, and so you have probably an intermediate layer that will kind of. I'm really designing this very badly, but the idea is that you're not, in order for that to work, you are talking to some intermediate guy that does a very simple function, and you have all your people querying, and they query to that, and this one will decide, well, this guy is free, so I'll ask him, and then he'll string back. The second time he gets a query, he will say, well, it's the same question, I'll ask this guy, because he knows, and these two are talking, so they know the same things. So this guy is replying now. And the third one comes in, and this guy says, oh, again, we'll go through that. So this is load balancing. It's balancing the load on the server depending on how loaded they are, how difficult it is for them to serve the services. Redundancy is also a thing here, because if this one for any reason fails, this guy here will say, well, that one is not responding, so I'll send all the queries to this one. complicated? Intuitively, it's very simple. Practically, it's quite complicated to set up something like that. In many cases, you have some sort of.
Got the cooling and everything like that as well. But
Say again?
you've got every other, you know, looking at it from the functional diagram, it's fine, but the actual practical implication, like you've got to add cooling systems and everything.
Oh yeah, of course, yeah.
Yeah.
That's why with IT, you kind of try and create layers of abstraction. So once you've done that, you only deal with one problem at one abstract level, and you want to make sure that your computing power is of 32 MIPS, mega instruction, million of instruction per second. And you know that this is what you can afford with your money. That's your limit. If you go beyond that, you need to know that you need to buy another computer that is parallel to that, and you buy it and you plug it in. So abstracting hardware performances from network services, and we'll come to that in the course of this week. It's going to be a.
Appears to be the first time that bureaucracy seems to work.
It's really funny you should say that, because that's so true that people are studying this. People are studying why the internet is such a complex system that it actually works, whereas we cannot seem to be negotiating much more simple situations in our daily life. So when you go to an office here, you're asked to do all sorts of stupid bureaucracy to achieve things. Anyway, it's an area of research. Understanding how it is that the internet really works is an area of research of information science. Okay.
Next project management seemed a cakewalk.
Security. You have the same problem. You have some information on a server, and you have your guys that want to use that information here. You have a protocol to negotiate that information. You have file formats to transfer that information across, and then another guy comes in and he wants to steal that information from you. Damn it. And if he knows the protocol and knows the password and knows the file format, that information is gone. So you want to be sure that the passwords are saved, and also that there are no breaches in the software, so that whenever you could go beyond the protocol and have the system crash and respond to you even if the password is not known or anything like that. There are all sorts of attacks that you can think of. Firewalls are software applications that control the flow of information on a network on the ground of a number of data, different data types that they have. So let's say that the firewall was here, the information would go through it only if the sender was a recognized IP address, say. So every other query coming from any other computer on the internet would be just disregarded. Your information is safe. You set up a firewall. They can filter on any type of logic. They open a packet, see if it's perfectly correct. If it's not, they drop it. There are a number of roles, but the idea is that we want to filter with a firewall what is the information that goes through it, with the purpose of guaranteeing the stability and security of your network. There are situations online when you want to put a number of these kind of intermediate clever boxes in between that will negotiate the different abilities that you allow onto the network. In a situation like this is an internal network, this is an external network. Everybody goes through this guy, and they all share the same access to these servers. In a situation like this, you can differentiate the access because external queries are coming from a different route than internal queries. So maybe a firewall here will be less restrictive It will allow for more protocols to go through, because you trust this network more than you trust the generic internet. Make sense? So the topology of the network that you set up is a function of the level of security, integrity, efficiency, and services that you wish to provide. I won't go too much into that, but there is a concept of DMZ, so a demilitarized zone, something that is kind of safe.
Bit excessive. Yeah.
That's what they call it. Yeah. Okay.
I just get a picture of North Korea, South Korea.
Cryptography. Are you happy campers when you go online and buy stuff?
No.
Yeah.
No.
Why not?
So obviously there's an element of risk.
There is an element of risk. True. We'll cover it now. What is cryptography? What do you know about it? Get that slide. It's meaningful for the time being.
Yeah, symmetric. It's encoding data.
Well, everything is encoding data. Every data
But that's
responds to some encoding, otherwise it's meaningless, right?
But it's, yeah.
So what specific type of encoding of data is it?
Sensitive data.
Well, no, if you go
It's,
back to the what type of encoding it is,
Protected, yeah.
it's protected. So it's data encoded in such a way that not everybody can successfully decode it, so transform it into information. Straightforward, right? Less straightforward to achieve than to describe. So, let's say, clever, huh? Let's say we have our hello 62 66 whatever. We know that this is transformed into, you know, each letter into a byte and so on. Everybody that knows this can go back from this to that. How can we hide this?
By
Changing these numbers, of course. How do we change those numbers?
by creating their own protocols and conventions.
Well, no, creating, well, because it's not, we don't want to destroy it, we want to hide it from people, so we want to be able to
So
take
create,
them out.
Yeah, so create a function.
So we could actually say, well, add 5 to all of them, right? Add 5, 62 becomes 67, and whatever it is. So the H becomes Z. So if I take it out, without knowing that I had to add 5, I get Z, whatever, P, Q, Q, R, whatever, and say, well, this doesn't mean a thing. But if I know that I've added 5, I go back and remove 5, and I get back to the initial information. 5 is my password. Okay? If I don't know that 5, I cannot get out the information. Of course, guessing at 5 is fairly simple, right? So I can try and brute force moving all of them up and down and see if a reasonable message comes out. Okay, so I try with 1, I'll try with 2, I'll try with 0, I'll try with 22, I'll try with 5, and I get hello. Oh yeah, I cracked this. All right. So symmetric cryptography is that cryptography that relies on sender and receiver to share a password. If we both know that password or that key, we can encode the information, transfer it, and then only the people that know the password can decode it. The more complicated the password becomes, so 5 is a very simple one, some passwords are more complicated, the more it's difficult to brute force its cracking. Now, when you go on your bank website, you asked the question earlier that says, okay, so what's this S? Well, this S means that you want security. And you feel free, you feel safer. You see sometimes a lock down in the bottom of the browser and say, oh, wow, this is secure. So I can type in my password or my code or whatever it is, and I know that this information will go there safely. But you never exchange the password with them to encode this information. Your computer doesn't know that password, right? So how can that happen? That's an interesting question. And that happens because your HTTPS protocol has agreed a password remotely with the server by asymmetric cryptography. And the way asymmetric cryptography works is that one of the two peers has such a clever system that uses one password to encrypt, okay, and a different password to decrypt. Okay, this is interesting. So what happens is that with the password that you use to hide some information, you cannot take it out. You need a different password to take it out. Okay? That's technically fairly complicated to explain. But for the time being, you need to understand this kind of asymmetry. Whatever you use to hide something is not enough to take it out again. So, when you get in touch with such a server, he will send you the password to encrypt, but will keep for himself the different password that it uses to decrypt. Okay? So, even if somebody can listen to the conversation, they would be able to encrypt the message because the password went across in clear, but they would not be able to take the information out. So it's as if you were given a box with a lock. They give you a box with a lock, you get the box with a lock, you put in the secret, you close it, you lock it, and you give it back. They kept the key to open it back. Make sense? That's asymmetric cryptography, where the password that you use to hide something is not the same that you use to bring it back. Okay?
Is there an example of that?
An example of that? What I just said. You're not even aware of that, but your client will be negotiating a password with your server to encrypt your information. So, make an example.
Like a bike lock, but one of the old ones. It's like one of those old bike locks, isn't it? Where you've got the keys and then you can override it. Is it one?
Similar, but I think the example of the box with the lock is much more matching, because in a sense you might be aware of the password to unlock it when you first receive it because it's open on the right key. It's a difficult example to make. When you go online on your Gmail, okay, it's an HTTPS address. It means that the conversation between you and the server is encrypted. You then have fields there that are your username and your password. But this is not the password that is connected with the encryption between you and the server. This is the password that you use to open your email. It's a different password. But you don't want that to be known by anybody else. So you want that to be encrypted as it goes towards the server, because we know that you're not talking directly to them. There is nobody that connected a direct cable between you. You are talking to a computer that is talking to another computer, that is talking to another computer, that is talking to Google. So everybody in between, if you were saying, my password is chow chow, my password is, everybody in between would be able to send, to kind of capture that information and then use it again in the future. So that's what you don't want to happen. So the way this is solved is that when the server comes in touch with your client, he will send you a password that you don't even see on your computer. You don't see it on the in the visual screen. You are completely removed from that. It's hidden from you. But that password is used to transform your username and the password that you're sending into a stream of data, 1, 22, 24, 72, whatever it is, that is meaningless to anybody that doesn't have the decoding password, which is different from the encoding password. So only the server that created that decoding password can bring it back and understand it. This is asymmetric cryptography. Everybody knows the password to encode, but that's not important because who cares? What is important for people is so that you prevent decoding. If you know a password that you use to know how to hide something but you don't know how to get it back, it's no use to you. You want the password to show, to reveal information. Okay? So, asymmetric cryptography relies on that. There might be a... is connected to some public key that you can use to hide this information, but only the receiver has this private key, private password to take the information out. Okay? The simplest example that I can show is the one I gave you before with the idea of the box. So everybody has available this box where they can put things in, and then the only thing they can do with that is give it to you. And you have the key to open it back and see what the secret was. Okay? I mean, if you're more interested in this, there's plenty. There's plenty. The past 60 years of information sciences are all about security. So I can kind of flood you with resources and information. The same thing can then be used to sign for stuff. This is clever. So you kind of reveal part of this secret. You reveal your public key so that people can try and see whether, and you're the only one that has the hidden key, and how do I make it simple? Well, we know that this process is asymmetric. So what the two passwords have different roles. So it's possible for somebody to kind of receive a packet from you and run an algorithm on it to notice that this information results in a security code, say 24. I'm not sure it's worth going through this. Okay, so when you have a private key that you can use to produce something that you can show that can only be achieved through that private key, you can get some data and do some cryptographic function on it, and that results in a short signature, a short number that can only be obtained with a private key, something that only I am retaining, okay? But can be tested to be valid with a public key. So, if I receive this packet of data from you, I get your public key and I try and see if I do the same check on the same data and I receive the same number. It means that you were the legitimate owner of the private key that you publicly state it's yours. So I have the assurance that you are the legitimate encoder of that package. Okay? Because only you will be able to give me that assurance, having the private portion of the private public key. Okay? There's plenty of videos on this online. I can point you to more resources. But the idea is that it's possible through cryptography, not all in a different way of ensuring the data is transferred safely, to kind of recognize that some data is actually legitimate. It is original. Okay? It's like the signature that you put on a document. Only you are allegedly capable of producing that signature. Okay? Now we are going towards really kind of borderline applications, but VPNs, virtual private networks. So I am on the internet here, and my office is here. And in my office we have 24 computers, and they're all connected and blah blah blah. Okay, so we are all on the internet. Okay, now here's the internet in between. These are physically connected to each other, and then there is a big gateway that is the internet, a big cloud, right? And I'm connected to my telephone line here. Now, an HTTPS server, so some server that is capable of encoding information between us, can be established here, and I could guarantee that I send information directly to that one if I was using that protocol. But if I want all of my communication, all of my systems to be cryptographically secure, what I can do is to set up a virtualized private network, which means that I set up a set of protocols between me and the client and the office, whereby all the packets that I send across are cryptographed before being sent, and then are extracted here and dealt with as if the computer was physically on the same network. So I could possibly, share a printer. If there was a printer here somewhere with that could, a plotter or anything, I could use that. Very elegantly, go back to slides. So I could make use of all the resources on this network as if I was physically local.
So like desktop anywhere.
Except desktop anywhere, it's not cryptographically secure, or potentially could not be. With desktop anywhere, you're only exchanging the graphical user interface. In this way, you're actually exchanging all of the resources, not only the graphical user interface and the mouse. Okay? And the difference is that computationally, with desktop anywhere, the computer is physically here, only the graphics are transferred across. But with this system, the computation actually happens here. And only the data is transferred across. So the graphic device is actually here. Everything is happening here. Only the communication is virtualized. So there is a big difference there, if you in a sense.
Yeah.
So desktop anywhere will have a physical computer somewhere here that thinks of a screen and then knows that the pixel should be of that color and then sends across the color of the pixels. In this other scenario, computer is here, screen is here, everything is computed on this side, the CPU workload is on here, because with desktop anywhere, CPU workload is on the server. Applications run on the server and so on. So it's much different in terms of where things happen. So virtualized private network are a way of encrypting everything that you do in terms of network over a transport that is inherently not secure, but you make it secure by sharing some passwords between servers and clients. So you are tunneling the information through something not secure and making it secure. There is a price you pay for that, because encrypting information here and decrypting information here requires computational power and requires extending the size of the packages. So encrypted information tends to be bigger than unencrypted information. So you have more bandwidth requirement to achieve that. Okay? And these are the protocols that you use to do that.
What examples would that be? Would that be like Dropbox, or would it be? Would it?
No. No, probably none of the systems you are using.
Yeah.
This is a way of
It's international.
physically
memory.
virtualizing your computer as if it never left the office. Okay? So physically, just as if it was in the office. So you have access to the very same resources, all the private network, and this can happen beyond the firewall and can happen beyond the DMZ. So the demilitarized is also. So in any way you can think, it's just as if you physically were in the office. This is probably the highest form of virtualizing a network. So it's the most complete, because every function that could be potentially possible from inside the network can be possible through that. But everything is safe, everything is encrypted. And we didn't cover TCP/IP quite completely. Every protocol comes with some limitations and some features. Through a virtual private network, you completely override all of them, and everything is transparent. Everything behaves just as if you never left the office.
Just a slow rate.
Like little slower. Yeah. Slower because there is 100,000 computers in between. But none of them will ever know what you're saying, because everything is completely encrypted.
So what happens to the IP address?
Say again?
What happens to the IP address?
And it's virtualized. You are assigned, you have a physical IP address,
Yeah.
and you get assigned a virtual IP address that is only valid inside that network, and inside your packages that actually are traveling over the physical IP address, there is a cryptographically secure virtual IP address that is exchanged only with the clients in this side. So nobody else knows of that virtual IP address. It's only valid inside this environment once it's across. So you are talking, well, you send a message to 10.0.0.1, and even if there is a 10.0.0.1 in this network, it's not the one you're going to talk to, because this one is going to be extracted and understood only once it's received there. So it's going to use the one that he believes is 10.0.0, which is another one. So it's like hiding everything that really happens into a packet, and then we exchange, and then you open it and say, oh, this is indeed a message for that kind of guy.
Seems easier said than done.
Well, it's easier done than said, I think. It's because theoretically it's quite complicated, but then practically it's just a matter of running a software on a client and a software on a server.
I meant the software. Easier said than done. So doing it from scratch.
Oh yeah, that's very complicated. And to be safe, there are all sorts of mathematicians that are looking into how secure is the protocol that you're using to encrypt and decrypt, and how easy it is for people to break it by brute force, by clever tricks, and so on. So that's plenty. I'm not sure whether I even need to reach to this level, but
Go on. Go through it.
just quickly, there is an inherent
It's
limitation to computing systems on a network whereby you call consistency the ability of all nodes to have access to the same data. Consistency means everybody knows the same. They share a consistent knowledge of the data. They all agree. Availability is the ability of surviving nodes to reach all of the data. All of the data is achievable by all nodes even when some nodes fail. And partition tolerance is the ability of different nodes to still have access to the data when the network is happens to have message loss. So you have the packets that we were discussing before traveling around. If you include the possibility that some of these packets are lost because then a cable was interrupted, because somebody stole it, because there is a software malfunction of some sort, that's partition tolerance. You can still cope with partial, unacknowledged message loss. And there is a theorem that says that you can have a system that has 2 of these properties, but not 3. It's impossible to have a system that will be consistent, so everybody shares the same data, available, so everybody can have access to all the data contemporarily, and that can be resilient and can survive if you have message loss. 2 of these, in either way, in any combination you can have consistent and available systems that cannot be partition tolerable. You can have partition tolerant networks that are consistent, but they cannot be available. And you can have consistent and partition tolerant networks that can available and partition tolerance network that cannot be consistent. Okay? So you can pick the 2 functions that you care the most and design the system around those. This is for systems that need to ensure real-time operations. When operation is not real-time, you can always do whatever you want. Sorry, it's not working today, try again tomorrow. That's something you can deal with. Okay? This is for real-time, consistent, available, and partition tolerant networks. Everything can be virtualized even more, so that you can think of a distributed computer system made of hundreds of CPUs and RAMs and everything that are actually perceived as one massive supercomputer. Okay? So this is a computer that was developed with gaming stations. Really. PlayStations, they are cheap because Sony subsidizes the hardware of the hardware to sell the games. So they are sold as cheap as you can get, and with some loss apparently on the seller, because they make a lot of money on games that they sell. So they want almost to give away the hardware for free to sell the games. So people started thinking, can I buy a lot of them and make a supercomputer out of them? And the answer was, yes, I can.
Do that soon.
No, they've done it already.
Is that at CERN, is it?
No, this is I think a US.
They do the same thing at CERN.
They're doing it all over the place because these things are very cheap and they are very powerful, and so let's do it. And so now new policies of these people is to try and sell the hardware with a couple of games attached to them because they want to make, they're not happy for people to buy them and then use them for some other ways because they are losing money. So next, you can think of the other way around. You can think of a single computer that virtualizes multiple desktops. So I can run one CPU and people can connect to that and behave on it as if it was a computer fully available to them, but it's actually running on a virtualized environment inside a computer. So maybe 3 or 4 people have their own desktop anywhere, being an example. Their virtual screen, but it's not that you have a real unique computer that you're using. You're using a portion of the computing power of a large computer that we have here at the university. Okay? So when you're connected to desktop anywhere, you're not really on a computer here. You are on a fraction of a computer here. So things can happen. When you're talking about computing and information sciences, it's all about virtualization strategies, and it's all about ways in which you present things that might not really be what you expect them to be. It's never over today. Okay. What are the commercial modes in which applications are sold? You are surely familiar with the old model of selling your software. You go to the shop, you buy your antivirus, and then you go home and you install it. Go to the shop, you buy Office, you go back home, install it on your computer, you use it. And this is working when people have their own independent computer that they can manage. The pro of that is that if you are a software company that manages to sell a lot of them, you make a lot of money because you develop the software once and you develop you deploy it to 100,000 computers. The cons of it is on the client side because you have to manage the whole thing. You have to make sure that the software does what you want, and then if there is a bug, you have to go to the shop, buy an update, go back, install it, and so on. A new way of deploying applications is the so-called SaaS, software as a service. So you don't buy the software, you buy a license to use a software that is on a remote computer, and you can count on these people to update it for you systematically. So Gmail being an example, you don't buy an email software, you don't buy it at all because it's free, but you kind of subscribe to a service that is kept up to date for you remotely. So you're buying a service. If you buy the commercial version of Gmail, you get more space, you get more features, you get more functions and so on, and you don't have to bother about keeping it updated every time a new release is done. Everything is managed remotely for you. Cons of it is that you need to be connected to the internet to do that, because if you're not connected, you cannot reach the service that you bought. Okay? So SaaS is software that you can use, and then contractually it can be for a year or forever, it doesn't matter. and people manage for you. They manage the updates, they make sure that it's always available, that so on.
Popularised with game and that was Steam and Valve.
Are they still not running on it's a complicated mixture of that, because it's based on sharing some local resources and some remote resources, I think, right? So you have access to
The recent games I've I think one of the recent ones I've installed is actually just pure server.
pure server.
Yeah, but I see what you're doing. I think that's the only one.
Okay.
The previous installation. They're ready buy games, but I bought that one. It was just purely on that,
Online.
on the Steam.
No,
But you've got to install Steam anyway, so I suppose.
it's mixed model then.
Yeah.
You have to install something and then you will deal with the service to extend and maintain and so on. It's a mixed model.
Rebuilding studio up there. That's cloud based.
There's plenty.
Yeah. Alright, sorry.
Okay, did you get this model? So it's a different commercial model of selling software. You have a server that deals with the clients, and you rely on people having already the client that they need. So maybe it's provided over your browser. So they assume that you already have a browser, and that's all you need. So you don't have to install anything special. Long day. So service-oriented architecture, it's a keyword that has been running around for some time. And again, it's the idea that you have some services online that you can access via a client that you have. So it's like splitting the services in a client plus a server. And it's designed to be modular, so it's flexible, reliable, extendable, and so on. Cloud computing is the current keyword. Everybody uses cloud computing in their marketing materials. It's all about making sure that the information is all available throughout a number of small services that you purchase a subscription to. And the idea there is that you can access that same service for multiple clients. So you can have access to your Dropbox files from your telephone and your computer and your iPad and whatever device you have, you'll have a different interface to achieve the same service. Okay? Application service providers are people that provide you software as a service solutions. APIs are agreed patterns for you to access functions of specific softwares. So we kind of mentioned the operating system at some point earlier. We said, well, my application will not deal with the hardware directly, will deal with the operating system that will provide ways for it to reach the underlying hardware. And that's an API as well. So it's a set of procedures that the operating system provides for the applications to reach some features. That can be valid of the operating system, but it can be valid of other applications as well. So I have a software that is running, and I deal with green energy building calculations. Okay, so you can send me a query through a specific custom-made API, so that we can exchange the core information that is needed for me to reply with some of the features that my software provides. So you ask me, I have such a building, it's this tall and this thick, and the location is Newcastle Central, and the orientation is southeast, and what's the temperature that I can hope to have in the room if I have this type of heating in the middle of December. And I tell you 22. Okay, this exchange happens through an application. An API, so an application programming interface. Okay? So you can write a software that makes use of some features that I Right. I think we've come to an end. Believe it or not,
Ha! No.
yeah, believe it or not, we are at an end. So this is the wrap-up. The wrap-up eventually is all about coming back to the initial slide again. We have covered today data and infrastructures. Now, we wish it was that simple. In the next few days, we'll be looking at people and procedures. And that's where you cannot write protocols. Because you can, if you write a protocol for a computer application, you can trust on it executing that protocol again and again, tirelessly. When it comes to people, you write a nice set of procedures that you should follow, and this is what you should do, and this is what you should do, and you should send an email like this, an email like that, and you can count on the fact they will not follow such procedures. So, people and procedures are a complicated bit of our work of optimizing building information modeling execution plans. But at least we know something on data infrastructure that we can count on. Okay? I think we got to an end. And I'm happy to take any questions you have.